Hello, and in this video we're going to make a linked list data structure in C. Now this will be the first sort of more complicated video of mine on C. The previous two videos I did were very basic. We covered memory allocation and structs and just very basic syntax. Today we're going to apply that knowledge and build the linked list, and a linked list serves as the basis for pretty much any algorithm or data structure that will follow after. It's a very useful thing to know. So if you don't know how a linked list works, I guess let's just start programming. I'll explain it as we go. So the first thing you'll want to do is create a header file. I'll just call it linked list.h like this. And how we create C programs normally is we define the public API functions in the header file, which we then include in other programs in the main executable or the main C file. And to prevent redefinitions, we do something like this: if and def linked list h. This can be anything really. And if this is a preprocessor if statement command, or rather a reverse if statement, if you could say that. And then so this kind of standard. Basically what this is saying is if linked list underscore h is not defined, so it's just a nonce constant, so we call it. If that's not defined, then we define this nonce constant, so it just doesn't have anything in it, it's just empty, but it's defined. And then this is the end of the if statement. So this prevents redefinitions. If we include one file multiple times, it won't give us a compiler error. Now in here we will include the sort of standard library header files that we will need, so just standard IO and standard lib for memory allocation. And another thing we'll need is a linked list node struct, which I'll just create a new header file for that. That doesn't even need a C file associated with it. That's just going to be a struct called node like this. And the struct node will have a pointer to the next node, because that's the nature of a linked list. So every node has some data and a pointer to the next node, hence linked list. And the data will actually be a void pointer, because a void pointer can point to any data type that we want. We could just cast it, so it can point to an integer or a struct or anything you want. So that makes our linked list universal. So the node, yeah, very simple data structure just like this. We will include it in our linked list header like so. And now let's actually define the linked list struct. So define it like this. We'll define a node pointer called head. This is the first element in the list. And then an integer value, which will be the length of the list. You could make this size t as well. That's just a bigger integer, but int is fine really. We will approach this program in an unusual enough way for C. It's more of an object-oriented approach, and you'll see how I'll do it in a second. The only two real values we need in the linked list is the first element and the length, because then the node contains the next node and so on. So first we'll make a constructor, so we'll just define the prototypes for all the functions we need. Constructor doesn't return anything, we just do init linked list like so, and then we pass in a pointer to a linked list struct, so we can set whatever values we want inside of this. So we pass it by reference, right? We define a linked list struct in our program, we pass it into this init linked list function, it initializes all the parameters inside of that struct, and then we can use it as a actual linked list. So this is the constructor. Now we need to define some methods, and how we define methods in C is we just create functions first. So the first one will be retrieve data, and the trick is to pass in a linked list pointer to every method. That's what we need. And then for the retrieve data function, we just need the index. So then void insert data, so insert doesn't turn anything. Logically paste this in again, but this time we need the index and the data that we want to insert, so that will be a void pointer. And now we need a void pointer remove data. And why this is a void pointer is or why does it need to return something at all if it's only removing it, is because of the nature of void pointers. So if this was a linked list with, say, integer nodes, right, where the data is an integer, those integers would be stored on the stack and be automatically deleted as soon as the program exits. However, void pointers are always pointing to the heap, and in order to fully delete a void pointer, we need to free it. So we will actually need to free the call to remove data, to remove not only the node from the linked list, but also the data that was in the node. Hopefully I explained that well enough. We need the index here obviously as well, and those are the methods. We could just leave it like this, but what I like to do is to actually define pointers to these methods inside the linked list struct, kind of like a C++ class methods. But this time we can give them whatever name we want, so say retrieve, and this is how we define pointers to functions inside of a struct, by the way, or just in general. And I'll do this, right? So I'll do insert and remove, and now we need to just copy the parameters as well these functions have. Remember, these all correlate to these function prototypes. Alright, and that's the header file all done. We have our function prototypes, and actually what I will do is I'll copy all of these 4 prototypes and create a new file called linkedlist.c, where we will straight away include linkedlist.h, which already has all the standard library headers included that we need. And up here in the comments, I'll just create a comment which contains all the function prototypes we need, so I don't have to refer back to the header file for that. So next, let's create the constructor first. So Alright, that's what I'll do is I'll copy this and paste it in, remove this semicolon, and now we can define the meat of this function. And it's really simple. So we just set the different parameters of the linked list. So length will be 0 by default, and the head won't even exist, so we don't need to set it at all. The functions, because they're already defined in the header file, we don't need to redefine them up here. But now what I'll do is I'll do this, and then we need 3 of them, and we will do retrieve, insert, and remove. The retrieve function will be equal to retrieve data. The insert will be insert data, and remove data. So now what we did here is we're treating the functions as variables, literally. So as we're able to do that in C, they're kind of the same thing, really, if you think about it. So we have this retrieve data function that's outside the struct, and we have this retrieve variable which is inside the struct, and it just has this really complicated type which is a function. So we're just setting this variable to this variable. That way we're creating methods, and this is the constructor, right? So this is the values, and these are the methods. Okay, next let's actually straight away create an important function that we need called iterate linked list. And what that function will do is it'll just go over the linked list for a certain amount of iterations to reach a certain index. And yeah, we'll be using that in pretty much every utility function for the linked list. Alright, let's begin with yeah, so it'll be of type, and it's static as well, because it'll be confined to this specific C file. It will return a node pointer, but the node pointer is a struct, so like that. Call it iterate linked list. For clarity and readability of code, we'll just use verbose names. The parameters, it will take the linked list pointer just like every other function. It will also take the index, and that's about it. Now it's very simple, just for loop. We'll define a node pointer called current node to keep track of it, and automatically set it to linked list head. And then we will do for, let's put this on the line, for int I equals 0. You can define I on top here for C99 compatibility, but I'll just do it like this. I is less than index I plus plus, and we don't even need these. There's just gonna be a one-line statement here. We'll just set current node to current node next. And we have to put these arrows because it's a pointer to a struct and not just a struct. And now we return current node. So yeah, very simple. That's it. This will return us the node that is at index. Okay, so sick. Now let's crack on with the methods. So we'll do insert data first. Insert data struct linked list, so that's the pointer as well. I'll just, yeah, I'll copy it here, then that. Alright, so first let's build error handling into this by default, so we don't have to worry about it later. If the index is greater than linked list length, or the index is less than 0, we can printf to standard error list index d is out of range, and insert the index, so this will give us a nice error message, and we'll exit with status 1 for error. Alright, that's the error handling all handled. Now let's do the actual insertion of data. So we need to create a node, because we can't just insert the raw data. And node, so struct node. This will be a pointer as well, so new node. We'll allocate memory for it on the heap size of struct node, like so. And we'll set the data, new node data to data, like that. So now to work out the next node, well, the next node doesn't exist, so we don't need to work that out. Now what we need to do is insert it as the next node to the current last node in the list. And there are two ways this can work. So our iterate linked list function is designed to handle anything with an index, or yeah, honestly we can just, no, what we need to do here is, even for efficiency's sake, I guess, we can do if index is equal to 0, alright, so okay, insert data, right? I got it all wrong. I was thinking of a queue where everything automatically goes at the end, but here we can have nodes anywhere in the list, so you just insert it right in the middle. But what if we want to insert it at the start? So in order to do that, we need to have a condition where if the index is 0, the new node next will actually be the head of the linked list, like so. And then the linked list head will be the new node. Makes sense, right? So the new node sort of moves over to the right, and yeah, so it's like that. Linked lists are extremely easy to sort of shift elements, and that's in obviously in quote marks, because we're not really shifting anything in memory. Everything is just pointed to. Now for everything else, we can just have a general statement where the new node next will simply be equal to iterate linked list we'll pass in the linked list. There's already a pointer, so we don't need to use the ampersand, and just index like that. So yeah, that's the next. So once again, we're quote unquote shifting it to the right, and now we can iterate linked list to retrieve the node that was before this one, before the index. So we choose linked list index -1, and we need to set this node's next node to the new node we created. That way we're inserting it into the list. And of course, don't forget to keep track of the length and increase it by 1 down here. Cool, now we have the insert data function all done. Okay, it's time to do the retrieve data function. Retrieve data is even simpler than insert data. Actually, it's extremely simple. It's a one-liner, but you need error handling, so it's a bit more than a one-liner if you include that. No, so the error handling is you can pretty much copy this insertion thing, but instead of having the index is greater than length, it has to be greater than or equal to the length. And yeah, that's about it. So now over here we could just return iterate linked list. So this will return a node, pass in the linked list, pass in the index. I copied the wrong parameters. Shouldn't have copied the data. So linked list, and we get the data from this node and return it. Alright, easy. So that's the retrieve function all done. Now the delete function, or the remove function rather. This one is a bit more difficult than the other ones, but nothing we can't handle. So once again, the error handling condition is exactly the same as retrieve, because up here, like, obviously we can add an element to the end of the linked list, so at an index that doesn't yet exist but we create it, but we can't add it, say, to an index above that. Then in here we can't retrieve an index that doesn't exist, we can't remove an index that doesn't exist, so all makes sense. Now let me just center this. First let's define some variables. So void pointer data, this will be what we retrieve, or rather remove, or retrieve from the removed node, should I say. Then we actually need the node, next node, and why do we need this? That's for because when we remove something, we need to keep track of the node after it, so we can set the next node of the node before the one we removed to the one after the one we removed. Yeah, hopefully that made sense. So first of all, let's handle index equals 0, because there are many edge cases with this. We want to get it right. So alright, if index is 0, think about it. The data, we already know, will be equal to linked list head and the data from the head, like that, simple. And now, so the next node will simply be equal to a linked list head next. So yeah, now we can free the linked list head because that's the node at index 0, and we set linked list head equal to next node. Alright, so that's index 0 all handled. Now we need an else if, because there's only 2 more cases. This is anywhere in the middle. If we do index equals linked list length -1, or rather, no, this is at the end. Anywhere in the middle will be the last else. So if index is equal to linked list length -1, this will be, so this at the end. Then this one's actually pretty simple. So all we need to do is set data equal to iterate linked list, pass in the linked list reference, pass in the index, retrieve the data from the returned node, and free, yeah, just copy this, paste it here. Alright, awesome. Finally, this is anywhere in the middle. The next node we can set to iterate linked list, pass in the reference, pass in the index +1, because this is the next node. Then the data will be equal to iterate linked list, pass in the reference again, pass in the index this time because this is the previous, or the one we need to delete. We get the data from that. Now we free out the node we want to delete. So copy this, paste it in here, and finally we set the next node. So what we need to do is, or rather, so set, what I mean by setting the next node is setting the next node of the node before the one we deleted to this node right here. So if we just copy this part and paste it here, but this goes to -1 now because this is the previous node, the one before the one we deleted. You know, we see the next of that to next node, like so. And at the end we just want to return data, so we can free that out if we want. Oh, and of course decrease the length of the linked list by 1. So now this is the API all done. We can delete this part, don't need it anymore. Of course we could make the this iterate linked list, we use it 4 times, we iterate over it 4 times, which isn't really the most efficient way to do it. We could save it into variables or modify the iterate linked list function to include the starting point in its arguments, but really that is a abstraction or an improvement that you can do in your own time as an exercise. Of course, if you're going to make this library public or use it in a project, you'd want to consider computational intensity. But I'll be right back. I'll write a test for this so you can see how this works. Alright, the test has been written. So it utilizes all the different functions from the linked list. We have here the constructor. You can see we just define a linked list struct called L. Then we initialize it by passing a pointer to L into the constructor. Here we have a for loop that goes from 1 to 10, or from 0 to 9 rather. And it creates memory or heap allocated integers from 1 to 10, because we're adding 1 to I. Then we're inserting them into the linked list in order. So then we have this function called list everything, which is just a for loop that runs through the entire linked list using the length value inside of the struct as a guide to how much we should loop. Over here, this is a bit awkward. It casts the value of L retrieve to an integer pointer first and dereferences it to get the value of it. So not the most beautiful looking syntax ever, but it's universal, so that's all that matters really. And a good C programmer will understand what's happening here. It's really not that complicated. Here we have a remove first element, so we remove element 0 here and we'll list everything in the list again. Now we remove the last element and list everything out again. So if we now compile it like this with the C file and main.c, we get no errors and no warnings. Now we run main, and I forgot to put new line characters at the end of my printf statements, but it looked like it worked. So if we compile it again, list index 9 is out of range. Alright, we didn't. I need to run a.out. So I can't main.c. I will put a printf here as well. We'll put a new line. It's more readable. Alright, so this after everything was added, so this looks fine. This when everything was removed, or when the first element was removed, so this looks fine as well. It looks like we're not updating it correctly, or rather, alright, we're using l.length, it's supposed to be length minus 1. That's the problem. So if we run a.out, we can see that the whole thing works. And just to show you that removing something from the middle works as well, because we didn't really test that. Remove middle element Let's remove, say, index number 4. So in this case, index number 4 will be 6. So 6 shouldn't exist. It should be 5 and then 7. And there it is. It works. So as a linked list, feel free to improve the iterate linked list function. That definitely needs improvement if you want to scale this to a big and resource efficient project. But the concept is there. I hope you learned something, and I hope you liked the video. I'll see you in the next one.